Hello there. Today we're going to talk about a topic really big in calculus called differentiability. Now, differentiability is a very easy topic. All it says is the ability. It's about the ability for a derivative to exist. That's it. It's just the ability for a derivative to exist. And we all know from the other days that the derivative finds slope. So today we're going to find out how can we tell, looking at a function, if the slope will exist at a point. And it is super easy. The main goal here is the main idea here though is talking about this idea that we call local linearity. And all local linearity says is if I were to graph a function, zoom in, I would get a straight line. And it's kind of easy to see, so I'll take a look at an example. Let's say we just want to look at the basic parabola right here. Like here's our basic parabola. Now, to see if a derivative exists, what we're going to do is we are going to pick any point on here. So I'll pick right over here around there. Now, if you notice, this is a parabola, so it's curvy there. Local linearity says if I zoom in at that specific point, if I zoom in enough, I'm going to get a straight line. And we can kind of see that. Watch what happens if I keep zooming in. If I keep zooming in, we still see that it curves, but as I keep zooming in, what's happening? It looks like the graph is bending, but it's really not. We're just zooming in so small that even the most curvy-licious graph looks like a straight line. And we're going to talk a lot about that later on today. So what we're looking for is a function that has local linearity. In other words, at an instant, it looks like a line. Now, in order to talk about differentiability, sometimes it's easy to find out where a function is not differentiable. So let's talk about that for right now. The first place a function is not differentiable is at what we call a sharp turn or a corner. So we say there are no corners. And the reason for that is because if I were to graph this absolute value graph right here, take a look down here. This is a sudden change. Now, anytime you have a sudden change in the slope, like for here the slope is -1, here the slope is +1. Anytime you have a sudden change, the slope cannot have local linearity. In other words, at this instantaneous moment, at x equals 2, this is not linear. It always looks like a V. And you can graph this on your calculator and just zoom in and see what happens there. So we say that no corners can exist. And that is because we won't have local linearity. And that's the reason for that, linearity. There we go. Another place is discontinuity. So let's talk about where a function is not continuous real quick. A function is not continuous. We already know this from the days before. In other words, we can't have no holes, right? No jumps. They're the Mac Daddy of them all. And no vertical asymptotes. So if we look at this graph right here, at x equals 2, we have a vertical asymptote. X cannot equal 2. In other words, at x equals 2, the value does not exist. So if the value doesn't exist, you can't find the slope there. Therefore, no slope. And we say not differentiable. Another one, a special one, is called a vertical tangent. Now remember, differentiability means that the derivative or the slope exists. And we can say that differentiability means that the derivative or slope exists. Well, think about this. At a vertical tangent, why can't the derivative exist? And it should be obvious, because the slope doesn't exist. At a vertical tangent, the slope does not exist. Therefore, this is not differentiable. See how easy it is? Now, very similar to that of the sharp corner there is what we call a cusp. If I look at this point right down here, this is called a cusp. Now, at a cusp is something very special. Let me graph this real quick for you. Let's see here. Let me go back to my graph here. I'm going to graph this for you. Doc D. Sometimes just got to clear it out. There we go. If I were to graph this here, x minus 1 to to the 2/3. Watch what happens when I zoom in really, really close here. Watch what happens as I zoom in really close. I mean, super close, super close, super close, super close. What do you notice is happening? Very much, now, like when I talk about the corner, if you zoom in, it always just stays a corner. Notice, we never get, at this point right here, it never becomes a straight line. At this one instantaneous moment, as a matter of fact, it's even getting steeper. It's getting worse. Oh my gosh, look at that, the horror of it all. It just keeps getting steeper and steeper and steeper and steeper and steeper. Okay, I'm bored with this now. What do you notice? It's just getting steeper. Matter of fact, at the cusp, at this point, the slope goes to infinity. And since infinity does not exist, the derivative can't exist. Therefore, not differentiable. So cusp are really kind of cool for us. So we like to say, no cusping in mathematics. So if we go back up to here, to this idea of local linearity, because we talked about it quite a bit here. Another way to think of local linearity, it says at this point, at a point, the slope of a line, of a function, I should say, of a function equals what we say the slope of the tangent line. Another way to look at it. So like when we go back to when we remember that parabola, right? Remember we looked at that parabola, right? If I look at a parabola right here, if I look right here, if I zoom in, this slope of this tangent line is equal to the slope of the function itself at that point. It's local linearity. Another way we look at this, another really cool way to look at this, is we say the slope going in equals the slope going out. The slope going in equals the slope going out at that point. We're going to talk a little bit about that in just a few moments. All right. So let's go ahead and kind of continue here. So let's take a look at an example. So for the example down here, we want to find out, list some values, one where the function appears to be not continuous. So let's deal with not continuous first. It talks about differentiable. Let's do one question at a time. Not continuous. Now continuity, we know that from up here, no holes, no jumps, no asymptotes. So if we look at the graph here, at question 6, at points x equals 6, it looks like we have a gap. So x equals 6, and that is because now look at here, what doesn't exist? The limit. Because the limit does not exist. And that's what we're going to say. The limit here does not exist. Now why does the limit does not exist? It's the jump. But if I ask you, based on continuity, which rule is broken, you better say the limit doesn't exist. Don't say jump. Is there any other place where the function's not continuous? And it doesn't look like it on the graph, but there actually are. At 10 and 0. At x equals 0 and 10. Why not? What's happening there? This is not continuous because why? Oh yeah, the limit does not exist. Remember, for the limit to exist, what has to happen? That the limit, as we approach a number from the left of a function, has to equal the limit as x approaches a number from the right of a function. They tricked us. So why does this limit not exist? Because there's nothing to the right. Why does this limit? Why is this not continuous? Because there's nothing to the left of it. So here the limit does not exist. That's kind of a tricky little question right there. All right, for part B, not differentiable. So where will this function not be differentiable at? Well, the obvious is x equals 6, right? And let's take a look at the reasons. Which one of these does it break? It breaks continuity, so it's not continuous. So because not continuous. Which rule is it breaking? Not continuous. Is there any other place? Yeah, it looks like x equals 8. What's that x equals 8? Because there's a cusp. Take a look at 4. It looks like there might be a vertical tangent there. So x equals 4, and that's because there is a vertical tangent. Some people say like at x equals 3, look at this right there, at x equals 3, they'll say, oh look, that looks like a corner. Some people might say cusp. If you get that wrong, we're not going to be too picky about that. And some people do argue at x equals 5 as well, because they say it looks like it might be a corner at 5. I always argue with that. I think it should be smoother, but that's just a graph. But if you make that, if it looks questionable, put it down. We're not going to mark it wrong. Now there are 2 more, and this is what I want you guys to write down. Make sure you know this. The derivative, and this is a big rule for us. The derivative or the slope cannot exist at an endpoint. Okay? A derivative or slope cannot exist at an endpoint. So we have x equals 0 and 10, and that is because they are endpoints right there. And that's a big one. You're going to mess this up so badly. Because remember, why can't it exist at an endpoint? You should remember this, and that is because the limit does not exist. Okay, we're going to talk a little bit about that here, okay? All right. So let's talk about the shorthand rule for differentiability, the shortcut. So for differentiability, here's what we're going to say. Okay? 1, f of x is continuous. 2, ready? The derivative from the left must equal the derivative from the right. Now what does that mean? Slope in has to equal slope out. And we're going to talk a little bit about that later on, tomorrow. We call this is what's called local linearity. Okay? That's that local linearity. And we're going to talk a lot more about this in the next video. Okay? Hope you guys enjoy it. Bye.